All right, what's up? Welcome back to Structure Free Chicka Chicka Learning. Thank you. Recorded live before a studio audience. So look, we're gonna answer why do we need interaction diagrams in this video for column analysis, especially when I have a cross section that's subject to axial load and bending. So let's consider the following cross section. Okay, so I need a straight edge, so consider the following RC section, and I'm going to draw what we might consider in beam analysis a doubly reinforced concrete beam. So here I have boom and boom, and I'm just gonna put I'll ignore drawing the stirrups to make my life a little easier. I have some steel down here, and then I have steel up here. Okay, I have steel like that. Okay, I have steel in two locations. I have some dimensions which I could draw out if I wanted right here, and we'll say that the loading, the way that this works, we'll say the moment, let's see, we're used to having compression here, mu, and then we'll have pu here, the axial load applied like this. So from a structural analysis, we determine mu and pu, and we have axial load and bending. There might even be a shear on this thing, okay? But we're not worried about that right now, because shear causes what type of stress? Shear stress, right? It causes shear stress, whereas m and the moment and the axial load causes normal stress. Okay, all right, good. So here, let's see, according to this loading, I would have, let's say, more compression at the top. So just for the sake of having labels, I'll call this AS prime and AS down here. Okay, now if I asked you, when we do an analysis for just a beam cross section, something subject to flexure, okay, how will we go and do an analysis for a beam cross section? So this looks like a beam, doubly reinforced beam cross section. Okay, so why don't you go ahead and explain the process for which you would analyze if this were a beam cross section. Go ahead. All right, so if this were a beam, okay, so forget that it's a column right now. If this were a beam, what's one of the first things that you would, what's one of the things you would need to do? Who wants to share some things that they would do if this were a beam analysis? Okay, so you might draw stress strain profiles. Great. Stress strain profiles, that's definitely something that we would do just to visualize the problem. Excellent. This is great review for the final. Next, what's something else? Does anyone else want to contribute? Apply force equilibrium. Apply force equilibrium. And why would we apply force equilibrium in this case for a beam analysis? To get what? To get A and C and A. For apply force equilibrium, get A and C and A. Major step, right? We did this in every beam analysis. We would have to find the depth to the neutral axis and the depth of the equivalent stress block. This was fundamental to all of our beam analysis. Everyone's good? Okay, good. Then what? You calculate nominal moment. How do we calculate the nominal moment? Calculate Mn using some moment equilibrium, right? We would use moment equilibrium. So apply moment equilibrium. And how many unknowns do we have in this problem? In this whole beam analysis approach, how many unknowns were there? 2. There are actually just 2 unknowns. Okay, what were the unknowns that you were thinking of? Which one? Mn is definitely one of the unknowns in our beam analysis. So there's one. What was the other? What's another? CNA. CNA is the other. Okay, those are our 2 unknowns, right? CNA, and then we can find A from A equals beta 1 times CNA. So I didn't even count that as an equation, but technically that would be a 3rd unknown, right? Even the strain at the steels would be an unknown that you would solve for. So you could have gone to 4 even, right? You've gone to 4, but that's based on the strain profile, right? So that's great. So it's basically our problems in beam analysis came down to 2 equations, 2 unknowns. Okay, but now we're analyzing a column. Okay, so let's say for this sake that the loading causes the following strain profile right here. Boom. And we know that it's going to fail in compression. So my compression strain here is what? epsilon c. My compressive strain here is what? Failure is, what value is this value right here? 003. Oh, yes. Yes, I was trying to think of the James Bond theme song, but I can't. I'm like, dun 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 dun. All right, so this is the ultimate compressive strain of 0.003, indicating that we have failure. I have here, boom. This would be CNA. I'm treating it like beam analysis right now. Okay, all right, that would be CNA. This would be my neutral axis depth right here. Okay, and let's see, I would have let's see here, my stress profile that you were, boom, I'd have this in compression, my equivalent stress block. Let's see, what else would I have? I would have maybe up here there would be a CS prime, a C sub C for the compression force resultant, and then here there would be a TS FS, the stress in the steel there. Okay, in the tension steel. That looks about right. Yeah? Okay. All right. And in beam analysis, it was great because the only thing that we had to worry about, and I will draw this in red on this side, was MN. That was essentially the unknown that we would solve for in beam analysis. But in column analysis, we have here PN also. Okay, and what happens is if we try to treat column analysis the same way that we do beam analysis, our unknowns would be CNA, PN, and MN. Those would be our unknowns. And so then what happens here? If we have CNA, we have 3 unknowns. How many equations do we have? 2. We only have 2 equations. And this is why we need interaction diagrams. And so the interaction diagrams tell us here's a possibility of all strain profiles and the PN and MN combination that would give us that. Only 2 equations, therefore need interaction diagrams for analysis and design. And design. It makes life a lot easier to have these. Okay. All right. Does that make sense? Okay. Why am I putting PN and MN? Why are they not drawn at the neutral axis? Why are they not drawn at the neutral axis? How come I am not putting PN at the neutral axis location? That green line right there. Why don't you go ahead and share with your neighbor, please? All right. Why am I not applied? Why do I not apply it about the neutral axis? Where do I apply it? Does anyone remember what it's called? Where does that load resultant go? It happens to be the geometric centroid here because my cross section is symmetrical, but it is also called the plastic centroid. So here we apply the loading at the plastic centroid. This is where we're going to measure our eccentricities. All right. Excellent.